So, jumping into things too much. I put up kind of an answer key to that midterm exam. So if you're kind of going through the points that I took off to kind of see what complete answers would be. And here's where, they might not be like the most written out, but it's kind of has, the details of what parts that you need for each one of these problems. You can kind of go back through those questions, try to figure out kind of where you were missing points, where, what parts you were getting wrong, what the complete answer would have looked like. So you've got that answer key up there if you're wanting to review kind of those midterm scores. I have not updated them because that post-exam question was set to be due before we met in class today. So I don't know if I'll have time after class today, but for sure tomorrow morning, I'll go on and get those exam scores kind of updated to include those points if you filled out that post-exam assessment. If everybody did it, puts that mean right at like a 78, right? I'll then have a better idea of exactly where kind of average scores in the class are right now. So I might report those on Tuesday's class as well. Okay. So we're leaving kind of that midterm exam. Last week, we started the next topic, which was nonlinear regression. We're going to finish that up today. I think we should get through all of that. I put up the next kind of stuff, the materials slides, just in case we have time. I expect we won't touch this until Thursday's class. So this week is going to be kind of a mixture of the nonlinear relationships we were talking about, and then the next type of nonlinear relationships we're going to talk about, which are interaction terms. So we'll probably start those on Thursday. We'll then use all these materials for next week's classes as well. Okay. So that's kind of currently where we're at. You know what? Let's do this. So today we're really going to be looking at a lot of review. And this is where I have to remind myself, I believe it was the score of the Colts game. It's here. This is 38.14. Should be that access code. So 38.14. Kind of come down here and start today's class off with this in-class quiz. Okay. So this should pop up under that week 10 quizzes tab. 38.14 is kind of the code that unlocks it. Okay. So we've touched on a lot of this already, but I want to do kind of a little bit of review, kind of what we've talked about. And then we're going to just take it a little, step further today, talking about these nonlinear relationships. Okay. So if we're thinking about which of the following are true, we can kind of work through each one of these possible statements. Right? So if I'm thinking about a linear model, we now have kind of both the linear and kind of adding a squared term or quadratic model. We also talked about these log linear, linear log, log models we can use as well. So the coefficient on the linear term, right, if we're looking at an independent variable, so I'm thinking about if I estimate a regression where I just have a linear term of this x variable, right? And I can still include a bunch of additional controls as well. If I instead estimate this relationship to include a squared term, I can still include additional controls. What's going to happen to the size of beta 1? Kind of a tricky question. So if I include a squared term, I'm picking up a completely different relationship. I have no idea what's going to happen to the size of beta 1. In fact, the sign of beta 1 could technically change. Right. So when I'm looking at that kind of independent variable, my x variable, the coefficient on the linear term from my linear model compared to my quadratic model, I have no idea what's going to happen. It could be the same technically. Yeah.
It's the code again.
38.14. Okay. So I have no idea what's going to happen to the coefficient. So if I'm looking for which of the following is true, I have no idea what's happening to that coefficient on the linear term. Could increase, could decrease. Technically, the sign could even be different if I had the right data set and the right controls. So what if instead I'm thinking about a linear log? So this is where I'm adding this kind of term in that it's always, right, going to be that we have a larger coefficient from a linear log model than just a linear model. So if I have this linear model, if instead I'm looking at what we said a linear log, well, then I'm estimating the natural log of that variable. So we said now the interpretation becomes what? When I take a natural log, I've essentially turned this variable into what?
Percentage.
Percentages. So the interpretation is now a 1% change in X1 causes Y to change by what? Beta 1. But remember, we're going from now essentially a percentage to something that we haven't touched. So we can think of this like a probability or a linear term. What do I need to do if I'm going from a percentage, kind of a probability? So how do I turn 5% into 0.05? I divide by 100, okay? Now you might instinctively think, oh, okay, well then the coefficient from the linear model is always going to be greater than the coefficient from the kind of linear log model. But that's not necessarily the case. So if I think about, let's say I had a scaled variable, right? Or where I had a variable where like the changes are in thousands, right? Well, if I had instead a 1% change, if I had something like GDP, changes by say $1, that's going to be a much smaller change than if I think about 1% increases in GDP. So in a situation like that, the coefficient likely would be kind of larger from this. Even though I'm dividing by 100, a 1% change is going to be a really, really large change. But the reverse is also true. Maybe I've got units, something like, oh, I don't know. What would be a good example where our percentage change would actually be? Well, no, we had something where, let's say I could see the units of something, let's say it was measured in millions. Well, 1 unit change in GDP, if it's measured in millions, would be an additional $1 million here. When I'm talking about a percentage change, what is $1 million in terms of GDP? A very small percent. So I don't really know what's going to happen. I might think that the coefficient is going to be smaller because I'm dividing it by 100 now, all right? I'm like scaling it, but I don't actually know, right? So we can't really say anything about kind of the size of that coefficient either. So the other ones, we can start to make statements when we're actually looking at things that tell us about statistical significance, okay? So if I have an R-squared model, if I'm comparing a nonlinear model, the R-squared will always tell me if that nonlinear model is preferred. Well, let's be careful. If I was comparing the linear to the linear log, I have the same dependent variable. Well, there, my R-squared would tell me whether or not my nonlinear model explains more of the variation. But what if I'm comparing a linear to a log linear? What did we say happens to the variation in y? I'm taking the natural log of it, so the variation in y is now different. In fact, I think we looked at like the sum function to actually show, oh yeah, we've changed the variation that exists. We could see R-squared go up or down. Also, if I compare this to a quadratic model, where I add a squared term, what will I always know be true? What will I always know is going to be true about the R-squared? When we add in a squared term, it's almost like I'm adding in an additional variable. So my R-squared has to be higher from that nonlinear model. So it won't always be the case if I'm looking at the nonlinear model that it's going to be higher. Sometimes it will. Like if I add a squared term, the R-squared will go up. But if I'm comparing it to something like a linear log, a log log linear or log, if I change that dependent variable, I don't know what's going to happen to R-squared. So what can I always say is true? If I'm comparing the nonlinear model to a model where I've included a squared or cubed term, we just said, what do I know will always happen to R-squared in that case? It always has to go up. It's like I've added new variables, right? So the only one that we can say with certainty here is going to be that my R-squared goes up if I'm adding these squared or cubed terms to try to capture this nonlinear relationship. Okay. I think we've got 5 minutes, so we should have plenty of time. You can see the answers. So if you want to make sure kind of you're getting this submitted before that time ends, we're still got about 5 minutes. Yeah.
Let's have the access code.
What's the access code?
38.8. Thank you.
Okay. So this is where I won't always use these quizzes at the end of class. This is me making sure you're in class. There's a lot of people not in class today. So if I'm thinking about this second question, right? If I look at the marginal effect of a nonlinear model, we kind of already touched on this, but I didn't quite go through it with the log or linear log or log linear relationships. In fact, I'm not going to push you as far to determine marginal effects from these log linear log relationships. But technically, if we allow this function to be nonlinear, that we said kind of the linear log, we had this depiction that looks something like this. What's the marginal effect? It's the change in my effect. So what's happening to the slope of my line of best fit? It is decreasing or it's changing. Before, when we were just estimating linear relationships, what is true about the marginal effect? It was always simply beta 1. Beta 1 doesn't actually tell us the marginal effect anymore. We can use it to determine the marginal effect at various points, but as soon as we make this a nonlinear relationship, the marginal effect actually depends on what? Well, my marginal effect from a linear relationship, it was the same for every x value. Now, what is the marginal effect? It's changing as values of x change. So any model we have that makes this a nonlinear relationship, our marginal effect is no longer constant. So if we're thinking about marginal effect of these nonlinear models, it depends on that x variable, or it depends on our independent variable that we've made nonlinear. Now, the easiest way to remember this, and the way that I will expect you to know how to calculate marginal effects, which we'll look at in Stata here today in a second, is if I have a squared term, what did I say the marginal effect became? So if I think about a model where I've got this variable, I included a squared term. We said essentially the marginal effect is what's the change in y coming from a change in this x1 variable. All I'm doing would be taking a derivative, right? So if I take a derivative of y in respect to x1, what do I get here? My marginal effect is beta 1, right? But then plus 2 times beta 2 times that x1 variable. So my marginal effect will be different for different values of that independent variable, okay? So the kind of adding the square term can kind of help us remember this, right? But what actually ends up being the case is that marginal effect varies for these other nonlinear models as well, the log linear. The math is a little bit trickier, so I'm just not going to push you as far as to calculating those different marginal effects. They will be different, but I'm just going to kind of keep it nice and easy. We only are going to look at calculating the marginal effects for this kind of squared model. Okay. Any questions over anything there? So once again, these are some things we've touched on, but kind of pushing a little bit more.
So you just took the derivative of the first equation.
Mm-hmm. Yeah. Right? What is the change in y? Right? Essentially, when we have a linear model, what would the marginal effect be? If I take a derivative of this function, all I'm left with is beta 1, which was essentially our interpretation of beta 1. It was a predicted change in y from a 1-unit change in x. It's just now a 1-unit change in x is going to have different effects depending on what the value of x actually is. Okay. So if I have some actual values here, so let's say this was 5, this was 10, right? What's the marginal effect when the x value, if I'm starting at the point where this is, say, I don't know, 10, right? What would the marginal effect of a 1-unit increase be? Well, this is still the effect of a 1-unit increase, but when that x1 value is 10, I'd be plugging in here, so I get what? 10 times 10 is 100, times 2 is 200, plus 5. My marginal effect would be 205. What's the marginal effect if that x value is only, well, here, I'll change it so that the numbers aren't as confusing. Let's say 6. Well, I'd be plugging a 6 in here. What do I get? 60 times 2, 120. There, the marginal effect is actually only 125. Okay. So my marginal effect will be different for different values of that x1 variable now. Okay. And all that's reflecting is there's changes in that slope of that relationship between x and y. Before, we were just allowing it to be linear. The marginal effect was always the same. Now, that marginal effect, or the slope of my kind of that relationship between x and y, we're now allowing it to be nonlinear, so it's going to depend on the level of x. Okay. Any questions over anything there? So before we kind of get to Stata, another thing that we'll kind of take a look at, and just so we have the equation ahead of time, we're gonna end up with these kind of interesting points, which is that I can sometimes have a turning point, okay? So how would I calculate the turning point or where this marginal effect maybe goes from being positive to negative? Well, if I have two positive coefficients, as long as that x variable is positive, will I ever have a marginal effect that's negative? No. But if they're different signs, I could. So let's just assume that maybe we have an x variable that could be positive or negative, or I could have coefficients that are different signs. How would I solve for that point where the marginal effect becomes positive or where it becomes negative, like where that turning point is? Well, all I'm doing there is setting that equation equal to 0 and solving for what that x value would be. That's the turning point. So if I do the math here, I end up with what? Oh, sorry, this is x1. Here's the equation that gives us our turning point. We have to remember, though, there's a negative sign in front there. Okay? So we'll kind of use some actual data and we'll see if we can identify turning points with marginal effects as well. So once again, a little bit of review to start off here before we actually dive in a little bit deeper. Okay? Any questions on anything here? Okay. So I had this idea that I introduced last week, and we did talk a little bit about how that marginal effect, right, for cities of different size, we're looking at COVID data, we said that marginal effect can be different for cities of different size. That's essentially what we just said here. The marginal effect will depend on that x1 variable. So we're gonna end up seeing, we can actually graph out what these marginal effects look like. I'll show you the kind of code and state it to do this. And I had kind of this other example that we kind of worked through, where maybe if I had the marginal effects here, there might be a point where initially for this x variable that we had of win probability added, initially it was positive, but there is a point where it then starts to become negative. Okay. So let's look at this a little bit more in depth. So we'll kind of get Stata going here. And I've got the do file. So we're going to jump down. So we kind of use some of these other examples. I've got my kind of global path set. I'm just going to come down here. And we're going to start with this happiness example. I'm going to use this a lot today, right? So I open this data set up. I don't know, happy was like a variable that somehow measured happiness. It was just 1, 2, or 3. So it's not like the best data ever, but at least it gives us something we can use, right? So I'm going to run this regression where I initially think about, okay, I've got hours worked, the number of children and age here, and I'm trying to predict what this person's happiness is, right? So I'm going to run this regression and I've got my kind of initial linear model. The R squared is 0.0018, not explaining a lot of the variation here, but we can kind of continue. Right? So I said there's really 2 ways of doing this. So I'm going to show you the first way, which I think is probably an easier way to do. So I'm going to, after class, post the next quiz today. I'm also going to, sometime tomorrow, I'm kind of finishing editing a few of the questions. I'm going to get up the next problem set. Okay. So if I'm thinking about that next problem set, I think it's probably easier, or what we're going to do, to create these squared variables yourself. Right. So I'm going to create children squared, which is just children times children, and hours worked squared. I called it hours squared, hours worked times hours worked. Right. Just creating the squared variables there. What I'm then going to do is simply add in the squared term for hours worked. Right, just for one of those variables for right now. So just so we kind of have it all on one line, I'm going to run the linear model, and then I'm going to run this squared model. Right? And then I'm going to make this a little bit bigger. We don't have to do as much scrolling. Okay. So what happened when I added in that squared term? What should happen to my R squared? It should go up. Sure enough, it went up barely, but it did go up from 0.0018 to 0.002. Now, my adjusted R squared, that would indicate the fact that it actually went up, right? Barely, but it did, right? It went from 0.0017 to 0.0018. What does that suggest to me? That the model where I included the squared term is explaining more of the variation, accounting for the fact that I added in essentially another variable. So which model would be preferred? Just using that statistic. Is it better to explain more variation or less? More. So this squared model or the quadratic model is doing a better job just using that one piece of information, which is the adjusted R squared. Now, a second thing we would want to look at to kind of verify, is this nonlinear model preferred, is we would want to look at, well, what's the statistical significance of that squared term? Is it statistically significant? At what levels could I say that it's statistically significant or different from zero? P-value is 0.02, so at the 90, 95, or 10 and 5%. So I've got some evidence that it's a statistically significant variable, that squared hours worked variable is statistically significant. And also the R squared are both indicating I should include this in my model, right? And those two things will often coincide. It may not always coincide, right? Sometimes one of those things would suggest you should use the quadratic model while the other doesn't, right? Now, usually those will be things where we have like p-values of like 0.15, so it's barely not statistically significant, but close. And so we still might see the adjusted R squared go up or vice versa, right? 0.09 is my p-value. Maybe the adjusted R squared just barely goes down, right? But those are the two pieces of information we look at to see, is this kind of the preferred model? Both of them here indicate yes. Hours worked, we should be including this squared term. Now, if I wanted to calculate the marginal effect, okay? So let's say I've got the squared term in there. The marginal effect will now depend on what the value of hours worked is, or what the value of that variable that I squared was, right? We had that equation that we wrote down. It was beta 1 plus 2 times beta 2 times the x variable. So what we can do, I can use this kind of display command. When I've run that regression, I'm going to use the coefficient on the linear term. I'm then going to add to that 2 times the coefficient on the squared term, and then multiply it by whatever I want to find the marginal effect for. So in our example, we're just pulling beta 1 from that regression output. That was the coefficient on the linear term. Beta 2, that was the coefficient on the squared term. But then our marginal effect, we have to make these marginal effect predictions for different values of x. So in this example, we would have used 10 and 6. I think in the example I've got in Stata, I'm thinking about someone who works 40 hours a week, right? So if I work 40 hours a week, what is the additional impact of working 1 more hour on my, what's our y variable here? Happiness, right? So if I compute this, right, I'm going to see that, okay, that marginal effect, working 1 more hour while I'm making money, that increases overall happiness of the individual. Okay. Now, because that squared term is negative, when I think about this marginal effect, because this is negative, as x goes up, what's going to happen to my marginal effect? So if this coefficient on hours squared is negative, if I multiply this by instead, I don't know, if I'm working 80 hours a week, well, I've still got the same coefficient value here, but now this one is going to be multiplied, this negative value is multiplied by a larger number. My marginal effect is actually decreasing. Maybe it becomes negative, right? So at 80 hours worked, I look at the marginal effect, and sure enough, now it's actually slightly negative, right? Well, just from this little kind of thought experiment, where would the turning point be? Somewhere in between 40 and 80 hours worked, right? I don't know exactly where, but I can calculate the exact hour at which the effect of working 1 more hour actually becomes negative, right? I mean, I like working more because I make more money, but at some point I'm working 80 hours a week, right? Working 1 more hour makes me less happy. So I can calculate that turning point simply using those coefficients as well. We said it's always going to be, right? And I forgot something here, right? That I've got my hours worked, but what should be in front of here that I forgot? So when we looked at this and we rewrote this to find the turning point, I need that negative sign, okay? So here, I need to make sure I include that negative sign, right? It's easy to forget that. That's why I left it out and wanted to make this point in class, okay? So -1 times the coefficient on the linear term divided by 2 times the coefficient on the squared term should tell me, hopefully it's somewhere between 40 and 80, right? So we'll run this, basically just having Stata do math for us. Sure enough, where is that turning point? About 74 hours worked, okay? Any number of hours before this, if I calculate the marginal effect, it'll be positive. Any number of hours past that point, it became negative. So I can kind of solve for where that turning point is. I can also calculate the marginal effect at different values of x. Okay. I'm definitely going to ask you to do this, right? On the quiz and on the problem set. Okay. Yeah.
This is more like a straight up question. Let's say like instead of always squaring, do like an I function or something.
So there's another way we could do this, right? I find this to be a little bit trickier, but if you want to, you can do this. I don't have to create that squared variable. What I can do is run that same regression, but I take hours worked and I use C dot telling it's continuous and then double hashtag. What that'll do is it'll include a linear and a squared term. So it'll do the exact same regression I had. So if I run this code, I'm going to see the same results as I did up here. So notice 0.0047, 0.0099. I'm getting those exact same values, right? It's just that now my squared term shows up like this. Right? It's still the squared term, it just looks a little bit different, which is why I don't like to use this, especially when I'm first introducing this to someone, because this is a little bit more code heavy and not as obvious that that is the squared term. But you would get the exact same results. Now, when you're using that display command, it also, there's an added negative effect or negative, not effect, but a negative, there's a con of using this method. Now, when I'm saying what that coefficient on the squared term is, it's just a lot more typing, right? I can call these variables something very short. Now I've got to put out exactly what that variable was. I have to include the C dot. I now only include one hashtag there. It becomes a little more confusing, which is why I always say the best way is just to create those squared variables for yourself, or the squared term yourself. But you could technically do that kind of using this additional kind of coding method as well. Any questions on that before we keep moving? I'm going to scroll up here, and just so we're not switching examples today, excuse me, I'm going to grab this code from up here. Okay? So I'll explain what this code does, but I just want to keep it so that we're kind of keeping this in the context of the same example. So I'm going to go back down here. I'm not going to use that second method, right? I'm actually going to just run that regression where I had that squared variable I created myself. So what you can do after you run your regression with a squared term, right? Actually, sorry, I can't do this. So I'll show you kind of the added, here we go. Why would I actually want to use the second method? If I can get this copied, there we go. So I'm going to paste it down here instead. After that kind of second method. So if I go back up here where I copied and pasted it from, notice I was using that more kind of complex version. This is something I'm not going to expect you to do when it comes to problem sets or the quiz. But you could graph out what these marginal effects are. As far as I'll ask you what the marginal effect is at specific X values. So kind of using this method will be all you would need to know. You could actually come up with a marginal effect in a nice visual depiction though. If I use this second method where I don't create the new variable, if instead of WPA, what are we looking at now? We're looking at hours worked. So that was our variable, okay? If I run this margins command, notice dy dx is essentially taking a derivative for me and then predicting what those marginal effects are at various values. So the first value is going to be the lowest possible value. This would be the highest possible value. This is the increments that it's going to create that marginal effect for you. So let's, in our example, let's say I want to know the marginal effect going from 40 to 80 hours worked. And I don't want a ton of numbers. So I'm just going to make this prediction in jumps of 1. So it's going to calculate for me the marginal effect at 40, 41, 42, 43, 44, 45, all the way up to 80, right? Now, if I do this, thinking, man, that's a lot of values. Also, it gets a little bit tricky because if I don't start at 0, 1 would actually represent the marginal effect at going from 42, 41, right? So it's a little bit trickier to read this output, but it does calculate the marginal effects for me. And if I combine it with this margins plot, and this is just some fancy code that will put like a nice line in there so I can see where that turning point exists. Now we all already know, oh, what did I do wrong here? I'll tell you what I did wrong. I forgot to rerun this regression, right? So if I rerun this regression, sorry, where I kind of use that syntax and then I run this margins command, that looks a little bit better. The marginal effect is initially positive, and then it becomes negative right here. Once again, the numbering's a little bit off. Remember, we said the turning point exists at like 74. Well, sure enough, 34 and 35 would actually be between 74 and 75, right? Because we didn't start at 0, we started at 40. So it gets a little bit harder to read these, so I'm not going to kind of focus on them. But I just wanted to kind of show you the power that you can have in Stata, which is, if I combine this with margins plot, I now get this nice visual depiction of, here's the marginal effect for every single hour's worked. So the effect of working 1 more hour if I'm already currently working 40. The effect of 1 more hour if I'm currently working 41, or 42, 43, 44. Sure enough, where is that turning point? Right around that 74 value that we found just using the turning point equation. So when it comes to using this do file for assistance on the homework, don't worry about this. I'm not going to ask you to plot those marginal effects. I just wanted to show you that you can. All I'm going to ask you to do is calculate marginal effects at specific values for X, or possibly solve for what that turning point is. This is just a nice visual depiction that kind of shows me, okay, yeah, that marginal effect starts out as positive, and at that 74 value, it becomes negative. It kind of shows me visually where that turning point would be. Is that clear what I'm saying there? I'm showing you more than what you would need when it comes to the problem set. Now, in order to run this margins command and margins plot, this is why you might want to use this other method, because when you create your own variable, when it takes a derivative, it can't identify that that squared is the same as the linear variable, so it doesn't know how to take the derivative of it. Because you've included just the same variable, but use this like double hashtag method, it knows that it should take a derivative in respect to the linear and the squared term of that variable. So the sake of what we're doing, I would maybe try to mimic more on the problem set what we did here, creating the variable for ourselves, okay? But I did want to kind of show you it's possible to do it another way, okay? Any other questions on this before we keep moving? Okay. So we're then going to come back and touch on what we did last class, right? If I had time here, well, we might come back to this if I have extra time. We can do an additional example. If not, which should be sufficient. So I'm going to create the natural log terms of some of the variables in this data set. So how do I do that? I simply take the original variable and I take the natural log of it. I can do that for hours worked. What values would I have to be concerned about if somebody would be working 0 hours? If I run this and somebody worked 0 hours, oh, 2 people work, right? So it's going to drop. I can't use those observations, right? So if I start to like run these models where I'm using the natural log of hours worked, it won't look the same in terms of observations as a linear model because I'm losing 2 observations here, which sometimes that's just a limitation of the data, right? I can do the same thing for happiness and the same thing for age. I'm just going to create these natural log variables. Now here, oh man, I've got a lot of problems. So if I look at this happy variable, all right, kind of what problem is existing here? Well, must have. So I've got, oh yeah, I've got some missing, skip past them now, there they are. I've got a bunch of missing values. I can't take the natural log of a missing values. So sometimes it'll kind of let me know, oh, there was already some missing values in that variable. Once again, just the limitation of the data. We're just going to act like, you know, we're just using the data that we could take the natural log of here. And then we did the same thing for age. Okay. So let's say I run this regression and I want to pick up on whether or not I should be estimating these relationships as linear or nonlinear. So I'm going to focus just on hours worked and age. Okay. I can do joint significance tests similar to what I was doing before, right? So here I've included both the linear term and the kind of nonlinear term. Okay. So if I run this regression, other than just comparing the R squareds of linear models to linear log, kind of like we did last class, I can include both the linear and the natural log terms. I can then look to see, okay, the statistical significance looks like not as quite high for the nonlinear terms. Okay? So I'm going to make a joint significance test to say, okay, should I be including these natural log terms? So for hours worked and age, I'm going to run so that test command did a joint hypothesis test. So if I run the joint hypothesis test here, should I be including, or would these added nonlinear terms have any joint significance? Well, if the p-value is 0.47, I start out assuming that there is no joint significance. Can I reject that? Not even close. So should I be including these nonlinear terms? This would suggest no. Okay. Now I could do the same type of joint hypothesis test, but for my linear terms. Hopefully this coincides with what I just found. So I just found the nonlinear terms I shouldn't be using. So what should be true about the p-value of this joint hypothesis test? Well, it should suggest I should use the linear terms. So my p-value should be small or below my alphas. So I can run this. Sure enough, 0.018. I can say that the linear terms had joint significance at the 90 and 95% levels. Now, once again, you can always use this method. There will be some weird situations where you can actually end up with both of these suggesting I shouldn't use the linear or the nonlinear terms. What would that actually mean? If I shouldn't be using the linear terms and I shouldn't be using the nonlinear terms, that's telling me that those variables likely have
No significance.
no significance. They shouldn't be included in my model at all, right? So if we start out, we're kind of assuming like they should be included in our model, but if they shouldn't be, we could actually end up with two results that suggest don't include either, right? But if we kind of find some statistical significance, like let's, for example, say I just run the model where I've just included the linear terms. So I just have age and hours worked. Well, initially I look at this and I'm like, oh, those are highly statistically significant. So then the next question will be, okay, they should be in my model, but should they be linear or nonlinear? That's when I would use this method to then determine, should I be including them as nonlinear or should I be including them as linear? And then allow those F statistic p-values to tell me kind of whether, which of those is correct. Okay. Questions on that idea? Okay. So once again, we're kind of reusing things we've already talked about with joint significance here. Let's say, so come back down here. So kind of, we didn't go through the slides here. We looked at these examples last class. If I did want to kind of look at this model comparison, I could use these joint hypothesis tests in a different example where I just test to see are the nonlinear terms both equal to 0 or are the linear terms both equal to 0. Okay. So just to kind of give us a different example of this, I will bounce back to an old data set real quick. So last class, we were looking at this GPA data. So I'm going to create the natural log of high school ranking. I'm going to create the natural log of SAT. And then I'm going to come down here to where I have high school ranking and SAT, and I want to predict their impact on GPAs. Now, we already looked at the results last class, and also just intuitively, is SAT and high school ranking going to be good predictors of what your college GPA are? Probably, right? So I know that they probably should be included. My question is, should I include the linear or the nonlinear terms, right? So I'm going to run this regression that includes both, right? I'm then going to test the linear terms, okay? So if I test the linear terms here, what does this suggest? That those added linear terms, should they be included or are they statistically significant or not? Yes, they are, right? every level. That p-value is 0. Now, if I run the same joint significance test, this is where sometimes it's not always obvious, because at what levels should I include the nonlinear terms? They're statistically significant at all levels as well. Which one do I choose? Right? Well, what's something else from these joint significance tests that actually would tell me that one of these is a better fit? Which one of these, looks like the p-values are both 0, but which one has more statistical significance? Is a test statistic of 73 more or less statistically significant than 22? More. So I have higher statistical significance from my joint hypothesis test for the nonlinear terms. So that's kind of like my tiebreaker. If they both look like they're statistically significant, this can happen, because SAT and high school ranking are such good predictors that even if I incorrectly identify as a linear relationship, they should still be included. However, what should I be identifying it as? Well, that nonlinear term joint significance is more statistically significant, so that's the one that I actually should be using. So if you ever kind of have this test where it suggests I should use both of them, say the linear term should be added and the nonlinear term, the tiebreaker is what has a lower p-value, which may not always be obvious. How do I know what has a lower p-value? Whatever has a higher statistic. Okay. Is that making sense? Or any questions on this? I know I'm not writing as much here today. We're kind of talking through more things, so make sure you ask questions if you haven't. Okay. Okay, where are we at in time? So what do I want to do next? We kind of talked through this idea, kind of looked through this happiness example. I want to show you the Davidson-McKinnon test, and then if we have time, I might just show you some additional examples of what we've talked about today. So another way of identifying whether or not what type of model we should use is we can actually run two different models, one that uses the linear nonlinear term, obtain the estimates from those models, and then include those estimates in the other one. So this, I think once we walk through it, will make a little bit more sense. So let's say here, I'm making the choice between kind of linear and linear log, or I'm making the choice between the log linear and the log log. Why can't I not compare the linear to the log log model? Because the dependent variable is different, has to be the same, right? So we can use this method either to compare the linear to the linear log, or the log linear to the log log. We can only compare two models if they have the same dependent variable. So let's go back to our happiness data. Where was that at? There we go. I'm going to open that back up. I'm going to kind of come back down here. I'm going to create all of my natural log variables. We're then going to kind of come down here to where we think about this Davidson-McKinnon test. Okay. So the first regression I'm going to run is simply using the linear term of hours worked. That's my linear model. Okay. When I run that regression, right, what I can do, let's see, can I get this all? There we go. I can use this predict command, and what it would do is go through them. I think we used this a while back, but we can use that to show what are we actually doing with our estimates or our coefficient estimates. We can come up with the predicted y values. So what I'm going to do with this predict command is for every observation, I'm going to come up with what from the linear model, what is the predicted value of y? Now I have the actual happiness, I have the actual y value. This is going to tell me what the predicted y value should be. So I'm going to come up with that prediction and call that model 1. That's my, I can type, linear model, okay? So I run that regression, I come up with these predictions. What we'll kind of see in the data is I now have for every observation, the predicted value from that linear model, okay? What I'm then going to do is run my second regression where I've got what type of model here? I've used the natural log of hours, so I've got a linear log model. Right? What I'm going to do is kind of run this regression and kind of save those predictions and call it model 2. If it helps, you could even call these models like model linear and model linear log, right? If it helps you identify a little bit more of what they are. So we've now got our predictions from both models. So the first part of that Davidson-McKinnon test is I go back and I run my linear relationship model, model 1. But I include the predictions that I got from model 2. If model 2 was better at predicting, then those model 2 predictions should have statistical significance, right? So I go back to my original model 1 and I include the predictions from my other model, okay? So if I do that here, if I look down at model 2, did those predictions from model 2, are they statistically significant? No. So that would suggest that model 2 is adding no additional explanatory power into my regression, which means that nonlinear model, which was model 2, should I be using that model? No. Right? Its predictions have no additional statistical significance. Now, I could do the same thing, but I could go back and I could run model 2 and include the predictions for model 1. Now, knowing that model 2's predictions were bad, essentially, what should the statistical significance of model 1 likely be? If I'm now running the nonlinear model, but including the predictions from the linear model, it's likely those predictions are actually statistically significant, right? So I can run this, and sure enough, what do I get? Oh yeah, now this is telling me that if I run the nonlinear model, that the linear model's predictions actually have statistical significance, or they actually are adding explanatory power. So that would suggest I should have been using model 1, the linear one. Now this won't always, right? It can always flip, right? In this case, the linear model is the one that's preferred. It could end up always being, the reverse is true as well. In fact, I think I've got one here. Yeah, let's scroll down a little bit because I think this gives us a slightly different way of looking at this. I think what I wanted to do, let's look at what I want here. So I'm going to so first of all, are there any questions on that before we keep? I'm going to give you another example of this, okay? So I'm going to scroll down here. I think I've already created this. We'll see. Nope, I hadn't already created the natural log of children. Now, obviously, I have a lot of missing values here because a lot of people have 0 kids. So I'm just going to run this command where I only keep the observations that have positive number of kids, right? So all of our kind of assumptions now are like, assuming someone has kids, is the additional impact of having one more kid positive or negative? Or what does that look like? So I'm going to do this Davidson-McKinnon test to figure out, should I be including children as a linear or nonlinear term? Okay. So my imagination would be like, as I have more kids, I don't know. If I had a 5th kid, the marginal effect on my happiness, I don't think would be positive. So my imagination is it's going to be a nonlinear relationship, but I don't know. Right? Maybe that makes me a bad person. But let's try to kind of do a similar thing, right? Here, I'll even change the variables just to make this maybe a little more obvious. So let's kind of save these predictions from our linear model, and I'll call them child linear. All right. Or I could call this like, this is my model for children, and it's from the linear model. Okay? So I can run this regression, and I obtain the predictions. Right? I'm then going to do the same thing, but I'm going to run what type of model here? Dependent variable is still happiness, so it's linear. Children is now log. So I'm going to save these predictions as from my linear log model. I then go back and run the initial linear model. But with my linear log predictions. And I'll save this and maybe update the do file here after class, okay? So if I run this, because what did I changed the name here. What did I call this? Model 2 was the linear log. And then down here, I changed the name just to be a little more clear to linear. So if I run this regression, the first part of my David McKinnon test, I'm running kind of this linear model, but I included the predictions from my linear log. Those predictions, are they statistically significant? Yes. So that would actually suggest that my predictions from the linear log model are statistically significant, or I should have been using the linear log model. So this is kind of the reverse of the other example we looked at. The other one suggests we should use the linear term. This one is suggesting we should use a linear log model. Now I still have a second part of that David, I always forget, is it Davidson? Yeah, Davidson McKinnon test, right? Which is if I run the linear log model, but include my predictions from the linear model, well, what are they also? Statistically significant. So here, which one would I choose? What do you think the tiebreaker is? Both have p-values of 0, but which one of these predictions were actually more statistically significant? I would not look at my p-value, I'd look at my test statistic, which has a larger test statistic. And this is where I have to be careful. I don't care of the sign, right, of my test statistic. I just care about the absolute value. So which one has a higher test statistic? That linear log model. So what part of the Davidson McKinnon test suggests I should be using the linear log model? It was a slightly more statistically significant when I included its predictions. Okay, so sometimes you will get kind of two parts of this test that tell you like, oh, you should be using both. Well, what's the tiebreaker if that's the case? Because in the first example we had, it was very clear, right? One of them, the predictions were statistically significant. The other one, they weren't. Here, both models' predictions have statistical significance. Which ones had stronger statistical significance? That linear log model. So if you're creating these variables and running these tests yourselves, instead of calling them model 1 and model 2, maybe it's easier to actually give them the name of what that model was, just to kind of keep things straight. But this is kind of what you would do. Okay. Any questions over this idea before we keep moving? Okay with this? I know this is a lot, right? So yeah.
Will the t-value always be the same for the, I guess it would be ln children and then the child linear log?
Not necessarily, right?
Okay.
Well, sorry. If I've included the same controls, then yes.
Just so we don't have to run both.
Right? Yeah, if you didn't want to run both regressions, those should always kind of flip-flop. It's a little trickier to do it that way than just running. I mean, it depends on every individual, right? If you can remember that, then you could always just know, okay, if the linear term has more statistical significance than kind of that the other model's predictions. But if we go back up, if those aren't necessarily the case, so like, there's my other models that we had, model 1 and model 2. Kind of notice here, so I've got, yeah, they'll just flip. If I can remember it that way, then you can do it that way. I see more people making mistakes if I explain it that way, which is why I just kind of show you running both models. But yeah, you can remember it that way, that's fine. Okay. Anything else I want to say here? Other questions? Okay. So since we already dropped that children equals 0 variable, I'm going to run the 4 different types of models just to kind of reiterate some things we talked about last class. So here I've got my linear model. Remember the way we name these models, it's the first variable is my dependent variable, the second is my independent, right? So here I'm looking at the relationship between happiness and children, linear log, log linear, log. Okay. Now when I'm comparing these first two, what statistics would I look at that suggest I should be using a linear log model or a linear model? I'd want to look at first what?
Squared.
My R squared. Gotta be careful. I want to look at my R squared. Adjust it. Now, technically, does it matter here? haven't added any new additional variables. I haven't added any observations. So really I could use either, right? But just as a fail safe, in case we go back to the quadratics, what is always better to do? Use the adjusted R squared. And we could even add that in at the very end. I can kind of, then we can compare using the adjusted R squared. So what happened to those? They both went up. So at least from the R squared or adjusted R squared, I should be using the linear log model. Sure enough, what's true about the statistical significance of the log term compared to the linear term? Much more statistically significant, right? 0.04 as opposed to 0.5. So two pieces of information, both indicate the same thing. I should use that linear log model. Okay. Now, here's where, can I make any statement about whether or not I should use that linear log or linear log or log linear model? Well, why can I not compare the R squareds? My dependent variable has changed, right? I'm now using the natural log, and so that variation is going to be different. So I can't compare these two models looking at my R squared or adjusted R squared. Okay? But in terms of the statistical significance of my coefficient, I could still compare that. I could use that as a piece of evidence of which of these models is preferred. So that linear log, I have that p-value of 0.04. My log linear, the p-value is 0.7. Which model should I be using? That would suggest the linear log, right? It has more statistical significance. Okay. And then kind of continuing down, if I'm now looking at the log model, if I wanted to compare it to the linear log model, can I use my R squared or adjusted R squared? No, they have different dependent variables. But what could I do? Compare the statistical significance of the coefficient, 0.04 compared to 0.28. So this would suggest, should I use the log or the linear log model? Linear log, right? It had kind of more statistical significance. So I can still compare across all four using that statistical significance on that coefficient between those two variables. I just can't use my adjusted R squared or R squared as like that second piece of information. Now, what could I do? If I'm between using a log linear or a log model, what can I now use as a second piece of information? I've got the same dependent variable. I can use my R squared or adjusted R squared. Which would it suggest I should use? Just barely, but it would suggest that I should be using the log model, which is the same thing. Is 0.28 better than 0.7? Yes, so I have two pieces of information both indicating I should be using the log model just compared to using that log linear. But if I'm choosing between the four, I ultimately would have arrived at choosing that linear log model. Okay. Questions on this idea before we keep moving? Yeah.
This may sound a bit funny. Why can't you just regress that one variable in both regressions and then use the R squared for that? Because it can't be changed or misrepresented by the other variables because they're different.
Include what variable?
The ones that were ln children and ln children on both linear log and then the other one, I think we're using log, right?
Yeah, so you're wanting to include both children and the log of children?
No, that's not right.
Or are you wanting to include the natural log of happiness up here?
Yeah.
Why can't I do that? If I have a y variable on the left side, a y variable on the right side, what's that statistical significance always gonna, right? I have an inherent relationship there, right? So it's really like I'm just rearranging the equation. All I've done if I do that is I've actually just scaled my y variable by some weird amount, right? I haven't actually, I've even just I've just transformed it, but in a different way than just taking the natural log, right? So we're not going to extend any further. You could technically make that y variable. I don't have to use natural logs or just square terms. I could make it any type of function I want. The only problem is the interpretation of those functions becomes like not practical, like in actual use. And so we generally stick to the ones that, well, it makes sense to think about 1% changes, right? Or percentage change in these variables, or to think about 1% changes in either the dependent or independent variable, right? Transforming it to be something weird, well, then I might have that the unit change is actually you know, 0.758%, or right, like, so that interpretation, my marginal effect becomes very difficult to convey to audiences and really doesn't have a lot of, it's applied econometric, there's not a lot of like applicable use to that, right? But you could, technically, you could scale either one of these variables to be whatever functional form you think. Doesn't just have to be a natural log or a squared. I could start adding in, you know, e to this variable squared divided by 2 times that variable. You know, I could do any type of crazy transformation. It's just the marginal effects aren't going to like have any real interpretation in terms of the real world.
So there's no way we can edit the regression how it is in order to be able to use the R squareds. Because we can't use the R squareds here because they're not related, right? Once the dependent variables are not related.
So nothing in this context of this class. If I wanted to, what would I need to have be, what would I have to have? I'm trying to think off the top of my head. I don't even know if there's a way I could do this, but what I would need is the variation in both of my dependent variables to be exactly the same. I don't think that there might be unique situations where I have categorical variables or integer values to where I could have a transformation that produces the exact same variation but changes the values. It would be very unique. So in most variables, I don't believe that would exist. I'd be amiss if I said off the top of my head. There might be some type of combination of variables to where I could keep the variation of my dependent variable the same, but it would be a very unique example if that was the case. Okay. Like I said, what this really hinges on is when I'm taking that natural log of the dependent variable, I'm inherently changing the variation that exists in it. So now all bets are off in terms of using that R squared or adjusted R squared. Any other questions here? Okay. Let me make sure we didn't miss anything. We've already talked about model comparisons. We did some of this last class today. We talked about interpretations. So just to kind of throw in like maybe a complete kind of summarization of all of this, what we're really looking for is when we force a relationship to be linear, if in fact it should be, and we didn't even talk about exponentials, we could do an exponential independent variable, but we did natural logs, we added like quadratic or cube terms even. What we're really doing is we don't have the correct functional form. So I drew some of this out for you last class, but if we force it to be linear, one of the key assumptions we had in our regression was that the expected value of our errors was equal to 0, right? So this was the idea that when I'm looking at my line of best fit and I'm kind of drawing it through this scatter plot, the expected value of my errors at every X value are equal to 0. If I instead have something that is non-linear and I try to estimate as linear, for some X values, I might only see positive errors. For some, I only see negatives. So depending on the value of X, my expected error will actually be non-zero. That was one of our initial assumptions going way back to like simple linear regression. So that's kind of what we're worried about. Forcing it to be linear, the expected value of our error term is no longer 0, which violates one of our initial assumptions, which is why we sometimes need to estimate these nonlinear relationships. Okay. In addition to that, just a couple other things I wanted to mention that I know we haven't touched on, but might pop up, wink, wink, on the quiz. Okay. So let's go, since we've already got this data opened up. Let's say I want to regress. Well, this is going to be a problem, isn't it? So I could do happiness. I could do hours worked. And I'm just going to kind of keep it here. So hours squared would be hours worked times hours worked. I'm just going to try to label these so it's kind of nice. So generate hours cubed would be hours squared times hours worked. And then hours quartic, which is to the 4th power. I I think that's right. That's where my English is not as good as my understanding of these numbers. So if I multiply the hours squared by hours squared, that would be the fourth term, right? You could create this a little bit differently if you wanted to. But here, if I'm thinking about a model where I now include, let's just say just the squared term and the cube term, and I'm going to control for age and children just so that I have kind of something going on here. So if I run this regression, just wanted to point something out here. Oh, I didn't run the actual variables. So let's do this. Okay. If I want to do this joint significance test, so let's say I want to test to see, we talked about this last class, I can see whether or not I should be estimating this as a cubed relationship or a linear relationship. How can I do that? Well, to get a cubed term, I also need the squared term, right? So I can use this joint hypothesis test for the squared and cubed term, right? Now, notice what it's telling me. So we said this F statistic is really coming from a different set of F distributions. So the first, we have 2 degrees of freedom. The first degree of freedom is going to be, how many variables am I running this test for? If I use the squared and cubed term, I have 2 variables I'm running the test for. And this gets a little bit more complicated, but essentially the second degrees of freedom is some function of my sample size. I believe off the top of my head, it's the sample size minus K, so the number of variables on the right-hand side minus 1. Don't hold me to that. I believe that's what it is off the top of my head. So I won't focus on this as much. I might ask you what is supposed to be a softball question on the quiz, which is this first number tells me how many restrictions or how many variables I'm trying to run this joint hypothesis test for. So in this case, I'm only looking at 2, right? If instead I run the same regression, but I want to look at the joint significance of all the added kind of terms, both the squared, the cubed, and quartic term. So now I'm going to include into my regression hours quartic. Right? Now, what should that first degree of freedom be? How many restrictions in my model, or how many variables am I running this joint hypothesis test for? 1, 2, 3. It kind of lets me know, okay, I'm now running this joint hypothesis test for 3 restrictions or for all 3 of these included terms. Okay. Now, what's that going to do is essentially the more terms I want to test for, I'm looking at different F distributions. Notice as I have more things that I'm testing against, same data, but my F statistic, right? It's more likely that it's now going to be smaller, right? My degrees of freedom is essentially getting lower and lower. Or shouldn't say my degrees of freedom. The degrees of freedom is technically the number of restrictions I have, but the number of restrictions I have is getting higher and higher, which makes my distribution kind of shape more varied. And so I'm seeing the same evidence, more likely to see a smaller value. All I expect you to know when you're looking at these results is that this first kind of degrees of freedom from your F statistic is telling you how many variables you're running this joint hypothesis test for. So that first degrees of freedom is just how many of these variables am I running a test for? In the second example, it's 3, right? The squared, cubed, and quartic term. Here it was just the squared and cubed term. Now, this is kind of an interesting one. Should I be estimating this relationship using the squared and cubed term relative to just the linear model? Well, is it statistically significant to add in those 2 terms simultaneously? Yes. So I shouldn't be using the linear model. I should be using a model where I've included the squared and the cubed term. Now, if I look at kind of where is that? Here we go. The statistical significance independently, not jointly, well, they have slightly different statistical significance, right? One is statistically significant at the 90, 95. One is statistically significant at all levels, right? But the joint hypothesis test says, is adding them in simultaneously, is estimating this as a cubed relationship relative to the linear, is that what I should be doing? For that, I need to look at my F statistics p-value. Now, if I include the 4th power term, compared to the linear model, should I be including the squared, cubed, and quartic term? What's my p-value? 0. So it's statistically significant at all levels. So compared to the linear model, should I be including the squared, cubed, and quartic term? Yes. But if I was gonna choose between these, right, just looking at those joint hypothesis test results, which of these has a slightly higher statistical significance? The model where I've only included the cube term, up to the cube term, sorry, or the model where I've then added in the fourth term? Well, the one where I stopped the cube term actually has a little bit more statistical no, actually it doesn't, right? The p-value is actually a little bit higher. So how many of, what model should I be choosing here? The one where I've included up to the fourth term. Right? So you can run these joint hypothesis tests for any number. I could go to the fifth, the sixth, the seventh power, whatever I want. Or like I said, we're not going to dive into it, but I could look at similar things for adding like in exponentials or different powers, even like to the 1/2 power of these different variables, right? And it'd be kind of the similar sort of concepts and ideas. I'll just limit it to us really just talking about squared, cubed, and I might give you something with a quartic term where I just want you to know what is the number of degrees of freedom. It's just those number of restrictions here, or the number of kind of variables I'm looking at the joint hypothesis test for. And then should I be using that model that included up to a fourth term? I'm just using the p-value from that joint significance test. Okay. So you're probably starting to see that the further we're getting into things, we're starting to get some answers here that are like a little ambiguous, right? There's not always a clear-cut answer, right? So that'll start popping up a little bit more and more as we kind of progress, especially once we get to like data issues. We're going to have a little bit more ambiguity, right? So I just wanted to kind of mention that here. It's as far as I would kind of take it. It's that fourth power, but I'm really just wanting you to use like a p-value from that joint significance test and identifying that that first degrees of freedom will be just the number of variables we're doing for the hypothesis test for.
So just to make sure, you can compare a joint significant test to just an individual one. So like if just the,
Well,
would you not?
what the joint significance test is telling us is a specific comparison. A comparison of this model where you've included the cubed, squared, and fourth term, only to the, if I leave those out, what am I left with? Just the linear term. So I'm only going to be able to compare this just to my linear model. I can't compare it to the one where I've only included just a square. Now, if I want to do that, what's a nice thing I could do? Well, let's say I included a model where I've only included the square term. I looked at the cube terms. I'm just going to run these so we can compare them real quick. And then one where I've included the fourth term. If I want to make the choice between these three models, what's true about the dependent variable? In all models, they are the same. So what can I now use? Can't use my R squared because I'm adding in additional variables essentially. So what can I use? My adjusted R squared. So what's happening? My adjusted R squared from the squared model, 0.0021, adding in a cube term, 0.0024. So it went up. So the cube, I've moved on. The squared model's shit. Let's use the one that has the cube term, right? Should I be using the one that has a fourth term? It's adjusted R squared is a little bit higher. That's actually the one that's the most statistically significant. That's the one I should be using. All right, so once we start to get thinking about adding in additional power terms, now I can go back to relying on making the choice between those models, just using my highest adjusted R squared. But I could also run a joint hypothesis test to compare it just to the linear model. That what you were asking? Okay. All right, so we should have covered everything that we need for that quiz. So that'll pop up shortly after class here. That next problem set, I'll get posted sometime tomorrow. I'll either post it pretty early in the morning. If I don't get it quite completely, there's a couple things I want to edit on it. I might post half of it initially just so you can get started on it. And then kind of replace the file so you have the second half of the questions. We'll try to change some of the data and some of the questions a little bit. So I just want to make sure I'm kind of double checking for typos. But you'll see that pop up. Okay. And then we'll be back at it on Thursday talking about interaction terms.
Lambert.